Hello guys, welcome to another video. Today we are going to prove this identity, and let me write in a more simple form. It can be written as 𝛿x of 𝛿f 𝛿y is equal to 𝛿y 𝛿f 𝛿x. Now the difference is obvious in both terms. Here we have the partial of the function with respect to y first, and then the partial of this part with respect to x, and here we have the partial of the function with respect to x first, then the partial of the function with respect to, then the partial of the whole term with respect to y. These and these are both the same, and these identities are normally used in undergraduate mathematics and physics, and today we are going to use vector analysis to prove this identity. This or this both are the same. And what theorems are we going to use today? Well, I have sorted it out, and we are going to use Stokes theorem, and Green's theorem. Let me first explain what is the Stokes theorem to you guys. Stokes theorem connects the curl of a vector and surface integral to the line integral of the vector, okay? And the statement of Stokes theorem reads: the curl of a vector surface integral through a surface S is equal to the closed loop integral or closed line integral of the same vector through a contour C. Now this contour C is the edge of the surface S, and we denote it by using C is equal to 𝛿s. This is the statement of Stokes theorem, and Green's theorem is basically the two-dimensional version of Stokes theorem. And Green's theorem reads Green's theorem reads that if we have a line integral m dx plus n dy, then we can rewrite it as a surface integral del n del x minus del m del y. I got a very little space here. This is dx, this is dx dy. I hope you guys can read it. This is dx dy. This is Green's theorem, and we are going to use this. Now let me begin by assuming a function. Let f be a function of two variables x and y. We are first going to take the gradient of the function. Gradient of a function is an identity. The del operator is an identity, and it is del x of something I cap plus del y of something j cap plus del z of something k cap. This part is empty, where we are going to put our function. Now for grad f, it is going to be del f del x I cap plus del f del y j cap. But del f del z is going to be 0. Why? Because the function is only dependent on two variables x and y. Hence the derivative of the function with respect to z is going to be 0, because the function is independent of z. Hence it is not changing with any change in f. This is the gradient of f, and now we are going to use a vector. What do we say this? Let's say it is also an identity or an expression. The expression is that curl of a vector which is gradient of a function is always 0 or the null vector. This is an identity in vector analysis, and we are going to use this to further our proof. And so we are going to use the grad f here, and we are going to write it down as curl of grad f. Okay, and since this is an identity, from this we can say that curl of grad f is going to be always going to be 0. Now, where else does curl comes in our proof? Well, curl comes up in Stokes theorem, and if we assume that grad f is equal to a, then we can rewrite this as curl of a is equal to 0, and from there we can conclude that this part of the Stokes theorem, this area, is equal to 0, and hence a dot dr is also equal to 0. Since this part is proven from here we say that curl of a is 0, we can say that this part is 0, and hence a vector dot dr, or the line integral of with respect to dr, is going to be 0. Hence, from Stokes theorem we say that a dot dr is equal to 0, which is from Stokes theorem. Say that a dot dr is equal to 0 from Stokes theorem. Now, a vector is here, and let's do a vector dot dr. Well, a vector dot dr is going to be, a vector is 𝛿f 𝛿x, 𝛿f 𝛿y, dotted with dx dzk cap, and this is going to end up, and this is equal to 0 from Stokes theorem, and this is going to end up looking like this: 𝛿f 𝛿x dx plus 𝛿f 𝛿x d 𝛿f 𝛿y, this term here, j cap I dot j is equal to 1, and 𝛿f 𝛿y dy plus, now since we do not have any k component, the k component is basically 0. The k component is basically 0, which is all equal to 0. Now this looks like the LHS of Green's theorem. The Green's theorem is here, if you can see, which is integral m dx plus n dy, and here we have integral some function dx plus integral some function dy. And now we are going to use Green's theorem, which says that if there is an integral m dx integral n dy, then it's going to be equal to the double integral, the surface integral rather, of the partial of n with respect to x minus the partial of m with respect to y, dx dy. And we are going to use this here, and let's see what comes out. We are going to get double integral partial of this with respect to x, and partial of this part with respect to x minus partial of this part with respect to y, and whole thing, surface integral dx dy is equal to 0. Now here we see that the total integral is equal to 0. Now, since we have from the beginning we have used S as surface and C as contours and dx dy's, and we have not used any specific terms for this, we have remained arbitrary in our proof. Okay, so all the integrands all the integrands, be it here this ds, this surface S is arbitrary, this contour C is arbitrary. We can take any surface, and any surface that is bounded by a line, a loop of C, that is bounded by a loop C, Stokes theorem is going to be turn out true. So hence, because we have remained arbitrary, we can conclude that since the integral vanishes and dx dy is completely arbitrary, hence the integrand of this part must be equal to 0. Hence we have proven this. Del x of del f del y minus del y del f del x is equal to 0, and therefore we conclude that partial of x, partial with respect to x of partial with respect to y sorry about that, partial with respect to x, and it concludes our proof. And here we have concluded our proof and proven. I always love writing that. And okay, what else can we do? Okay, we can write this in our initial form that we have used, and let me use that right away. It is 𝛿²f 𝛿x 𝛿y 𝛿²f 𝛿y. But I really love this form because here you can see the difference between these two. Okay, here you can see that the order of derivative is not same. It is visible here, but it is much more subtle here. And so that's the end of the video. We have concluded and we have proven this identity, and hence we are free to use it in any possible situation. And why don't you guys go and assume a function f is equal to some arbitrary function. Okay, let me give you a function f is equal to 3x square sine of y, 3x square sine of y, and try this. Take the derivative with respect to y first, and then take the derivative of the remainder with respect to x, and see what comes out, and then do the derivative in this manner and see if the both turn out to be the same. And have a good day and keep doing mathematics.